Okay, guys, good morning, everybody. Top of the hour, we'll get started. Stereochemistry. I also have quizzes in return for the Thursday group. Friday group, I'll give them to you this afternoon. We will meet upstairs. Alkene reactions. Got a little bit to finish up there, though. Last time we were looking at hydrogenation, reaction of alkenes with hydrogen to make alkanes. When we hydrogenate, we double bind, we end up with an alkane. Two H's there. Hydrogenation, is that a syn addition or an anti-addition?
Syn.
Syn addition, yes. Same side from the metal. We looked at the idea of exothermic, and if looking at two different reactions, which would be more exothermic? It was this reaction, right? Because this starting material is higher energy than this starting material. They're both going to the same place, that one drops more, right? That same idea is just shown over here by a table from a textbook. All three of these alkenes can give the same alkane by hydrogenation. They all give the same product. Which reaction will be more exothermic? Well, it's this one, because here this alkane sits the highest, and when it falls down, it falls the most. It gives off the most energy. Of course, you got to understand why this one sits highest, right? Etc. But we've already covered this. That's just the alkene substitution pattern. So that's just a repeat of that up there. We can maybe ask a couple other questions. Which has a higher heat of hydrogenation? What is H of H? H of H is the amount of heat that's giving off when you do the hydrogenation. Now if we list it as a delta H, if it's given off, delta H would be negative. And the more it gives off, the more negative. And the more negative, that sounds like it's lower. Whenever we just call it an H of H, it's actually a positive number. We're just saying the amount of heat that's giving off. And so the more heat it gives off, the higher the H of H will be. So we're not quoting it as a delta H, we're quoting it as an H of H. Which will have a highest heat of hydrogenation? That is, which will give off the most heat when hydrogenated? Which one contains more heat? That is, which one is least stable? So most stable would mean it's lower in energy.
So the cis one?
This one.
Yes, cis. Which one's higher in energy? Cis, because these groups are sitting there, I don't like being next to you, so that's high energy. This is higher energy. So when both of these are hydrogenated to butane, both become butane, but this one gives off more heat. It has a higher heat of hydrogenation. Hopefully pretty straightforward, yeah? Okay, while we're here, let's look at a couple other miscellaneous questions about alkenes, not related to heat of hydrogenation. The one on the top right is a little bit, I believe, possibly apples and oranges. Let's look at it. Which reacts faster with HBr? On left or right? Because data, real-life data, not make-believe, real-life data from the lab tells us that one of these reacts 100,000 times faster than the other. So which one do we theoretically predict to be faster?
I'm going to guess the cis one, or the one on the right, because doesn't have to move very far.
Because of stereochemistry.
This is a little complex question because it's more towards apples and oranges. We've got multiple things going on. Anybody have an argument, though, that you'd like to throw out? Anybody see anything that you can maybe, you're a lawyer and you're trying to convince someone. Give me a piece of evidence. Yes.
I don't know if this means anything or it's stupid, but if it just has to move one little notch over as opposed to across the whole alkene bond, would that make a difference?
Not sure what you mean by one notch over.
Well, the ones, the cis side, oh, that's, yeah, the cis side is just right next door as opposed to the trans side. That's my guess. I'm a very bad lawyer.
I feel like trans would be faster because it's lower energy.
What do you mean trans would be faster? The other one is, which one is trans?
I would say the one to
The one to the left is trans, but the one to the right, it sounds like you were thinking the one to the right is cis.
It's not cis?
I thought.
No, the one to the right is, cis trans not applicable to the one to the right. The one to the right is not stereogenic.
Oh, okay.
I'm still gonna say the one to the left.
Anybody? If this reacts with HBr, what type of cation are we going to form? Tertiary. If this reacts, we're going to form
No, secondary.
secondary cation would form. You see it? Tertiary cation is much more stable. So if it's much more stable, it's going to be easier to form the tertiary cation. That's kind of the answer. It's the one on the right, much faster. Here's the reason I don't like the question. Because the cations are different. This cation is going to look like this. This cation is going to look like, either way you go, it's going to look like this or there. These cations are not the same. So if you plot this, you got two different cations. This is A, this is B. A would be better, correct? Now if we were starting at the same point, which would be easier to get to? A. Problem is we ain't starting at the same point. Are these the same starting? No. And it's kind of hard to tell because they're both di-substituted in terms of two carbon substituents. But one it's on sort of here and it's trans. And so that's why it's a little bit complicated. But I still have seen this question out there, and I think it's the fact that it's a tertiary is your simple answer, but to me, if you think about it, it's like, well, hold on. Okay, let's move to the one below. The one below is more straightforward. Both of these reactions actually give the same product. Which reaction is faster, though? When this reacts, what type of cation are we going to get? Tertiary. What will it look like? It'll look like this, right? There's a new H there. Okay, tertiary. When this reacts with HBr, what type of cation are we going to get? Also tertiary. Same exact cation if you think about it. Please make sure you think about it. Okay? They both give the same cation. Because that's how you get the same product. Then the Br minus adds to the cation. You get the same product. Isn't chemistry amazing? Did you see this coming? Yeah? Y'all here? Okay, so if we come over here and plot it, as opposed to just getting it all jumbled in our mind, let's plot it so then we can step back and look at things. They're going to the same cation. Let's call that C. Okay? Let's call this A, B, and C. Yeah? Do they start at the same place?
No, isn't B lower in energy?
Can we tell? Which one's lower in energy? B is lower in energy. So over here we would put B here and A here. They're both going to the same place. Which one's going to get there easier?
A.
Was somebody ready to say B? Because it's more stable? No. A gets there easier. It's already kind of halfway up the mountain. A gets there easier. Okay, you're climbing Mount Everest. Who's going to get to the top of Mount Everest easier? This guy or this guy? This guy is going to get there easier from a given starting point. It only has to take a couple of steps, then it's at the top. Much easier. Easier for A to get up here. A is going to react faster. A reacts faster. Please use your reaction coordinate diagram to simplify and get your thoughts together. Yeah? Question?
Can you explain why B is lower energy?
Well, I'm not going to explain. I'll refer you back to the alkene discussion of alkene stabilities. All right? Alkene stability. Actually, when we covered that, I told you, I kind of looked at my watch and said I think it's like 9:20. Remember when we covered this? Okay. So that's just a couple of other miscellaneous because we're near the end there. Like we said last time, nobody's hydrogenating butane to make butane. That's just sort of going backwards. Here's an example of when you would use an alkene hydrogenation. And the synthesis, what is this, Propecia? Anybody? Is this Propecia? Yes. A synthesis of Propecia. You pick up here to here, they're making this other ring, but when they make it, it gives this alkene as a result of this reaction. But ultimately, they don't want that alkene. They want that to be an alkane, just saturated. Because they want just an alkane. And to get that, you got to add an H here and an H here. They drew the one in that they added because there's stereochemistry here. Over here, they didn't worry about it because there's no stereochemistry. Two H's is added. How do you add two H's? They're hydrogenating that double bond. Because this is where they want to get rid of a double bond because it just happened to end up there with this type of reaction. They're using platinum. This is in the form of platinum oxide. Sometimes you can use these metal salts. Hydrogen will reduce this to platinum metal and you form your catalyst sort of end the reaction. There's an example of a hydrogenation. You can also, over here, here are a lot of your sort of cholesterol hormones, cholesterol-based hormones, testosterone, etc. You'll learn all these in biochemistry. Testosterone, right here. By the way, the "-one" ending, because it has a ketone, testosterone. It's also got an alcohol, but it's sort of the ketone takes precedence. In the body, particularly the male body, testosterone is reduced to dihydrotestosterone. Two hydrogens have been added, dihydro, right here, and two H's, and this becomes saturated. Okay? Now your body doesn't use hydrogen and platinum catalyst. Your hydrogen has very special enzymes that will do these reactions. Okay? But still, we can understand the transformation, the terminology. Maybe you don't call it a hydrogenation biochem because you're really not using hydrogen. But we can call it a reduction because the molecule is being reduced. You can understand the name, why there's these two hydrogens, testosterone, those two hydrogens have been added. So when you look at structures, you can sort of see why the terminology makes sense. The enzyme that does this is called 5-alpha reductase. Reductases do reductions. So here's sort of an application. Now, DHT actually leads to, high activity leads to some problems. It's high activity in the hair follicles leads to hair loss, and high activity in the prostate leads to prostate growth and perhaps eventually prostate cancer. So some drugs actually inhibit this enzyme. So in the male body, this is not produced as much. Okay? So you're inhibiting this reduction of this double bond. And Propecia is a drug that does inhibit this enzyme. Propecia is used for hair loss. The same compound is also used to treat prostate growth, but it's not called Propecia then, it's called finasteride or something. It's the same compound though. And it does the same exact thing. So, a little biochemistry and pharmacology type application. One last thing over in the alkene handout. How do you do a hydrogenation? Hydrogen's in a gas. What if we were using a gas in lab? I mean, this week, yesterday you guys weighed out a solid to do your reaction at the very beginning. What if it was a gas? Well, obviously you can't weigh out a gas just like on the valve. It's going to be okay. When you do hydrogenation, it's done in an apparatus. I have one in my research lab. Here's a photo of it and some description of the different parts. So if you're interested, you can take a look at that. I'll also have a little video, maybe we'll show it one at some point, but that's just the hydrogenator hooked up to a tank of hydrogen. It's got a shaker, so instead of stirring your reaction, it shakes.
Shaking, not stirring.
Yeah, it will be doing that a little bit later. You've seen that in the lab. Okay, we'll plow ahead. We'll see what type of questions are. Alkene reactions. Those are your alkene reactions. You got that puzzle?
Mm-hmm.
Yeah?
Olefins never forget.
Stereochemistry. In lab, we looked at the idea of chirality. We looked at determining R and S. We introduced optical activity. Very bottom of the purple sheet. Enantiomers rotate pp light. One enantiomer rotates one way, the other enantiomer the other, equal opposite. And our next lab will actually be the polarimetry. Okay. Now, I'm pretty sure this is what we're going to do. We'll confirm this next week. No lab next week. We're talking about 2 weeks from now.
Oh, you're not going to come in for lab?
Pre-lab that week, we will go over the more on the optical activity. This section here. Please though have looked at it, because if you ain't looked at it before, you will be probably confused. Okay? Please have looked at those topics in your textbook, and then I'll give you my version of all of that. Okay? Today, though, I want to move on down to Roman numeral C, Fischer projections. At this point, I'll ask any questions about stereochemistry up to this point. What we've covered thus far. Are you ready to move ahead to Fischer projections? Fischer projections also part of the lab we're currently doing with the dibromide product. Okay. Fischer, we'll see this name a good bit. There's a Fischer esterification in organic 2. Fischer, a very prominent scientist of the 1800s. Assign RS to each compound below. Okay, RS.
S.
How did you get S? Start with the largest compound.
Bromine is
The first one.
chlorine is next, and then the methyl.
And what's the lowest priority group?
Hydrogen.
Hydrogen. Is it in the back? Is it in the front? It's in the plane. So what did you do with it in the plane? If it's in the back, you just whatever you get. If it's in the front, you reverse whatever you get. What do you do when it's in the plane?
Move it.
So you got, whoever said S, how did you deal with it?
I didn't.
I switched
Be honest, I
bromine
didn't
and
do it.
hydrogen, and that gave me an R configuration, and because I had to flip those two, I converted it to S, because it flips as well.
Oh, that actually sounds like a decent strategy. Yeah. I've never really heard that, but did you read that somewhere? Okay. Whatever works for you. I'll show you a different way. My way is going to be based on Fischer projection. Because Fischer projection is very useful. By the way, if it ain't useful, I probably ain't going to be talking about it. Right? That's the way I am. Okay. I said next show each in a Fischer projection. Or should we do this first? I'm actually recommending you do it first. What is a Fischer projection? It's another way to draw these. You remember when we did Newman projections, it was another way to draw the compound? Newman was useful because we were able to see things a little bit differently. Well, Fischer is the same way. A Fischer projection, we use crosshairs. Boom, boom. Okay, it's supposed to be just a crosshair. There you go. You got a carbon with 4 substituents. But when you see a crosshair, it's supposed to mean something. The things on the side, okay, are coming out. Like cat whiskers, or like a bow tie. Things at top and bottom are going away. That's what the crosshair implies when you see it in organic chemistry structure. And you just have to know that. That's what it implies. Okay, how do we get to crosshair? We're going to look at this guy, and we'll also need to do maybe model. I'm going to tell her to do it, and I'll go back and redo it, and we'll talk about it, but I'm just going to plow ahead. I'm going to stand over here, okay? Actually, I'm going to stand over here. Because I want to stand so that the things on the side are coming towards me or away from me? Towards me. That is, I want to, when I draw, the things on the sides are coming towards me. How do I stand so that's the case? I want to stand over here. Okay? If I look through here, the things on the sides are coming towards me. And the other two things here are going up and down. So if I'm looking through here, what's going straight up?
The methyl and the hydrogen.
The methyl.
Okay.
What's going straight down in the board? Now, it's not coming straight down like this because there ain't no bond angles at 180 when you're dealing with a tetrahedral carbon. But it is coming down in the plane of the board. And if we consider as sort of, this is my view here, right through here, from that horizontal, the methyl is going up, but the H is coming down. But they're also going away from me. Because really, my little guy needs to be standing sort of like this. And the ground is like this. And so if the ground is that way and we're perfectly standing up, we sort of got here. And the methyl and the H are both behind the board. If the board is straight up here. Or if just the vertical is straight up. Now the Br and chlorine are coming towards me compared to that vertical. And they're also on the sides, because if I'm over here, the chlorine's coming towards you. It's bolded. So it's to my side, to my right. And the bromine, because it's dashed, is going behind the board. If I'm over here, behind the board is to my left. And that's the answer. The chlorine is to my right if I'm over here, correct? Okay, we'll just draw it. As if, what do I see? I'm drawing what I see. Chlorine to the right. Bromine is over here. Here's the compound drawn in the Fischer projection. Let's make a model and see if it, here, we got a carbon and H. Here's the compound. Carbon coming straight up. Little H there. Bromine, chlorine red coming towards you. Bromine green going back. Okay, is that the compound, the original compound? Chlorine red coming towards you? Yeah? Okay. Here I am over here. First off, I'm going to turn this just so these two on the side are not coming down, but they're straight towards me. Boom. Now they're straight towards me. Now what do I have? I see a chlorine on my right. Is that what I drew on in the circle? I see a green on my left. Bromine. Is that what I drew in the circle? I see a methyl going straight up, but is it also going a little away from me? See how it's leaning back? It's at the top, and top means it's going away from us. And then I see a little H that's going straight down. But isn't it also going a little away from me? Okay. I just drew this on the board, and now I'm able to look at it like this. And there it is on the board. Because things on the side are really coming towards us, right? Didn't we say that's implied? The methyl it's up, but it's also going back. The H is down, it's also going back. So, there it is on the board drawn in a different view called a Fischer projection. And if that's all we were asked to do, then boom, there you go, full credit. As opposed to maybe having the chlorine here and the bromine there. That would be the enantiomer reaction. Okay? Now, is it R or S? Now let's start fresh, clear our mind. It's much easier to do R and S here. What's high priority on this carbon? Bromine's 1, what's next? Chlorine 2, carbon 3. How's the H? Going back. You know what? Okay. So with the low priority group going back, what is it? Counterclockwise, yes. Over here, okay, boom, boom, boom. Too much in your mind. Much easier to see here. And you know how to draw a Fischer projection. Question?
So, since in the drawing is saying that bromine is going back, and the,
No, bromine's coming forward,
and the Fischer,
correct?
but in the drawing it's shown as back. So does that?
Well, I mean, it's just like over here. The bromine was green. I drew it on the board. From you, the bromine's going away from you. But the Fischer's now turned, because the Fischer is now turned. And if I show it like this, the bromine is actually now coming towards you compared to the carbon. So it's just turned a little bit. But it's still the same compound. And that's hugely important. We just drew the same compound a different way. Okay, there we go. How about over here? Can you draw Fischer over there? By the way, can you tell something about these two compounds, the way they're drawn? Yeah, they're drawn as mirror images. So, but that's kind of cheating. Do it from the beginning. Let's see. I would stand over here. That way, the things on the sides, as I'm looking through here, we're going to look through here. All right, you get the idea? We're looking through there. Things on the sides are coming towards me, but they're also on the sides. Fischer, I got one carbon with 4 things. What's going straight up? Methyl. What's going straight down? H. What's on my left if I'm standing over here? Chlorine, because it's coming towards you guys. So it's on, if I'm looking at it, it's on my left. I'm looking at it here, it's on my left. The bromine's got to be over here. But is it? If I'm looking at it, bromine's on the right, so it's going back. Well, just turn. I'm looking at it, bromine's on the right. There it is in a Fischer. Yes, it is a mirror image of that. Actually, you look at the Fischers. You can tell they're mirroring Fischers. 1, 2, 3. H is in the back, correct? What is this? R? Yes. Those are 2 enantiomers of that compound. Do we have an outline? Yeah, I think we need to have, there's an outline somewhere, isn't there? Or what?
This is what it is. It says out. It says out.
Okay. Okay. I'm just remembering something a little bit differently. But everything, all the information I think is here. The other is just a white miscellaneous. Okay, I think we're good. All right, let's go ahead. That compound only has 1 chiral carbon. What about compounds with more than 1 chiral carbon? Okay, and this was sort of just a new Fischer, but RNS is there. How many stereoisomers are possible for the following compound? This guy here.
4.
How many stereoisomers possible
4.
for this compound?
2 chiral carbons.
How many chiral carbons are here? 2 chiral carbons. If it only had 1, how many possible stereoisomers would there be? 2, R and S. Like the previous example, that compound had 1 chiral carbon, 2 possible configurations. Well, how many for this guy? Okay. The answer to this question is 2 to the n. That's an n number. And that is equal to maximum number of stereoisomers. For a given compound. What is n?
The number of
Number of chiral carbons? Yes, but that's a little bit too specific.
Is it stereogenic centers?
Yes. N equals number of stereogenic centers or sites. An example of a stereogenic center or site is a chiral carbon. Are there any other stereogenic centers or sites? Yes, an alkene can be stereogenic. Not all alkenes, but some can. Right? How many possible stereoisomers for this compound? How many chiral carbons? None. But how many stereogenic sites are here?
1.
1. The entire alkene is a stereogenic site. N is 1 here. And if N is 1, what is the answer to the maximum number of stereoisomers? 2. So what are they? That's one of them. The other one is barrier 2. So an alkene can also be a stereogenic site, but not all alkenes. That's the video and the alkene stereogenic, etc. Chiral carbon is just one example. So how many stereogenic sites here? Two. It's the two chiral carbons. There's no other. So 2 to the 2 is what? 4. So the answer to this specific compound is 4. But that's maximum number. In some cases, there may be less. And we'll get to that. But you can't have more than 4. Okay, draw all 4 of them. We're going to draw all 4 as perspective drawings, and then we're going to draw all 4 as Fischer projections. Can you draw all 4? Well, let me get you started. Once you see what we're talking about. Pretty straightforward. Boom, boom, boom. Because this is very generic here. How about if I draw... Also, we want to kind of leave room here because we're going to do below. So actually, let me sort of make some room and move this up. Boom, boom, boom. Let's make that one a particular projection, and let's make this one a particular projection. How about that? Is that one? Are there others? Well, based on our little math equation thing, there should be 3 others. How about if we go boom, 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 and make this one bolded, and make this one dashed? Is that different? Or is it just the same thing redrawn? How about if we go boom, 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 make this that, and make this that? How about that one? What would the last one be? See how much more? Is this it? Basically, we have 4 different configurations. We've got to be careful though moving forward. Are these all indeed different? Let's move ahead. We'll eventually have to look at that. Okay. Before we go any further, let's do R and S. Here it's very generic. You can't do R and S. That's just sort of your connectivity. You have to recognize that we can then take it further and look at these specifics. RS here. Oxygen 1, carbon with chlorine 2, carbon 3, H in the back. What is this? R. How about this? Chlorine 1, carbon with O is 2, carbon is 3, H in the back. What is this? Both of these are R. Chlorine, H in the bag, yeah. Yeah? Okay, you got the others done already? You should have, because that's the same, so that's R. This is different, so that's S. That's different, that's S. This is the same, that's S. That's S, and this is different from that, that's R. Here we go. I cheated. Did I get them right? Because if we don't change the backbone, if we change bold to dash, that should be S. And if we change dash to, bold, let's just confirm, is this indeed S? Chlorine 1, carbon with O is 2, methyl 3. Uh-oh, it's clockwise.
The H is.
But the H is forward. And if the H is forward, we just reverse clockwise to counterclockwise. S. Yes, they should all be right. Okay? Are any, based on RS, are any of them the same? I've got an RR. None of them are RR. So that means they're configured differently. Unless, we'll see. Okay? All right, what's the relationship between these four? Are they all stereoisomers?
Diisomers and enantiomers.
Let's start with stereoisomers. Broadest category. Are they stereoisomers? Sure, they all have the same connectivity. They all have the same name because what is the name of this compound? I'm not going to name it like an alcohol, but if we just name it as a butane, we have what, maybe another hydroxy group, what, 2-chloro, 3-hydroxy butane? Does that name make sense? Are they all that? Yes, they are. They all have that connectivity. This one you would just call what? R, R. Because stereoisomers, you only distinguish them by what? Some type of stereochemical descriptor in front of the name, right? Okay? That's RR. What would you call the one on the end? We have to, maybe here you have to learn how, which do you quote first? So typically this refers to the first substituent. So it's actually RR. This one would be SR. But that's, don't worry about that. What other descriptor could we put in the front of this? Assuming we knew a little bit more information, what other descriptor? Let's come back to that.
D or L.
Let's come back to that. Okay, what's the relationship? Let's number these 1 through 4. What's the relationship between What's the relationship between 1 and 3? Relationship between 1 and 3. I heard a couple people saying enantiomers. Anybody else? Why is 1 and 3 enantiomers?
So it's the exact opposites.
Because when you look in the mirror, like this, your mirror image is going to have its left hand up and its right leg forward. Everything's going to be reversed in the mirror. Yeah. 3 is enantiomer. As long as it's different. Remember, everything's got a mirror image. I agree. 1 and 3 are mirror images. But are they different? How can we tell if they're different? How can we tell that they are enantiomers? What did we look for? We look for Waldo. Does one have a plane of symmetry? Much easier to see plane of symmetry with Fischer projection. Because these things are kind of twisted. It's like, well, no plane of symmetry, but hold on, what if they lined up? Now you have a plane of symmetry. Fischer projection. Let's draw this in a Fischer projection. And we're going to draw it below here. Okay. I got two chiral carbons, so I'm going to have 2 crosshairs. All right? And let's just look at this guy. Okay? There's an H going back. I'm going to stand over here on the ground and look through here. These are the 2 chiral carbons. This is here. Verticals. All right? I'll number this, see if this helps. 1, actually the 1 position is coming the other way if we do it officially. 1, 2, 3, 4. So I'm actually, because I said this is the ground, 1 is near the ground. 1, 2, 3, 4. 1 is near the ground. Here's the ground. 1 is near the ground.
Do you know, I mean, does it matter where you stand? Like in the last problem, you stood to the left, and this one you're standing.
I want to
right.
stand so the things on the side are coming towards me.
Okay.
If I'm over here, the things on the side, the OH,
Yeah.
because it's coming towards you.
Yep.
It's coming towards you, so it's on my side if I'm over here, and it's coming towards me compared to the carbon. See how it's coming towards me?
Yeah.
Okay, let's do this. What's on carbon 3 going straight away from me?
The methyl.
Methyl. We can draw this methyl in. Methyl. Okay? This sort of needs to be connected, right? What's on carbon 3 coming towards you, which is my left?
Hydroxy.
The OH. It's on my left. What's on carbon 3 going behind the board to my right as I'm over here?
Hydrogen.
I'm drawing hydrogen. Okay. Now let's look at carbon 2, the other carbon. Which side is the chlorine on? The things that are projections, those are going to be the things on the side. Is the chlorine, which side is the chlorine on? Chlorine's on the right. I'm drawing H here, methyl here. Okay,
Yeah, explain that to me. I don't get it.
here we go. I've got to, if I'm over here and if I just bend down, that is here, and look through here, the chlorine is on which side? Coming towards you, it's on my left. But how is the thing in the plane going? Straight towards me. The methyl, right? This is what the methyl coming towards me. But the methyl needs to be going away. That's what this means. With the methyl going away, the chlorine's on the right. How do I make the methyl go away? I come over here and stand.
I see.
Over here, with the methyl going away, what side's the chlorine on?
Right.
It's coming towards you guys. That's my right if I'm over here.
It's always going to be perspective from the carbon coming to you.
We make sure that the methyl's going away, because that's what that means. With the methyl going away, chlorine's on the right. Here we go. There's a Fischer projection for the first one. Now, we can confirm if this is right. Here's one way to confirm. Do R and S here again. This should be R, because we're drawing the same compound. Is it? Oxygen 1. Carbon with chlorine 2. Methyl 3. 1, 2, 3. Oh, it's counterclockwise. That's S. But how's the H? It's on the side, which means what? Cat whiskers. Also, the side is like it's hugging you. Things on the side are coming forward, correct? With the low priority group is forward here. Forget about it up there. We have a new drawing. Counterclockwise, but the low priority group is forward, so what is it?
It's reverse.
Reverse it to R. Yeah, it's the same thing. The R configuration of these here. What is this down here? Chlorine 1, carbon with O2, methyl. It's counterclockwise, but H is forward. Yeah, they both are. It's the same exact compound. We can check ourselves. Okay, do the other three. Okay. We can cheat. But that don't help you, because if you're starting from fresh, you can't cheat. Here we go. What's the difference? Well, the carbon of the OH is the same. So there's no difference there. But this carbon is different configuration. How do we get the different configuration? We can put the chlorine here and H here. This will be RS. See, now we can kind of cheat. I'll cheat on the next one, then you can do the other one on your own. But let me cheat on the next one real quick. The next one is just the opposite of the first, right? Everything's changed. That means that the OH is going to be here and the H is here. That means that the chlorine is here and the H is there. because it's SS. Practice. You need to practice and be able to get to this point. Make sure you can get it from scratch. Also, make sure that's SS. It should be. This is SS. Here we go. 1 and 3. Are they mirroring each other in the Fischer? Are these mirroring each other in the Fischer? You see how they're mirroring? Okay. When they're in the Fischer, though, you can more easily find planes of symmetry. Because it's right through here now. Trust me. Can you divide this in two? Is that a plane of symmetry?
Nope.
No. Is that a plane of symmetry? No. There's no plane of symmetry. What does that tell us about the mirror image? Enantiomers. 1 and 3 are indeed enantiomers. We'll pick up here. Please do the fourth one. What's the relationship between 1 and 2? And then the